is higher order mutation. My interest is genetic programming, but the talk actually covers a number of techniques. So what we're going to be looking for is, we're looking for higher order mutants which are hard to kill, but also don't change the source code over much. So when you go to higher order mutation, there's a possibility of making larger changes to the source code, and what we want is relatively small ones. So the approach is going to be multi-objective, trying to get mutants which are both high quality but also not too different from the original source code. I'm going to talk a little bit about how we use genetic programming. There's some results on poor benchmarks, but I think I'm going to probably just concentrate on the work on Jesus at the end. There's some results on the coupling hypothesis, and that's a slide on non-deterministic mutants that we conclude. So you're all supposed to shout at me and ask lots of questions. So I've been reminded that I should point this out to you. So what we're trying to do is a multi-objective approach. What we want is mutants which are both difficult to kill but also don't change the code ever much. So the point of this animation is, along the x-axis we've got a number of test cases where the mutant is different from the original source code. So if you like, this is the goal. We want to get programs which are only fail on a small number of test cases, and simultaneously we also have another goal, which is we don't want them to be overly different from the original source code. So this animation is showing members of a genetic programming population, which is what the lots are, and the red line is highlighting the Pareto front, is highlighting the individuals which do best on both objectives. So it's a genuine Pareto approach. Either you can do well on the x-axis, relatively poorly on the y, or vice versa, and you'll still be on the Pareto front. So the Pareto front is, though in the jargon, those mutants that are non-dominated. And you can see that we initially start off with large population back up here which do poorly on both objectives. And as time progresses, the population tends to move down towards this corner, but also we have individuals which are doing very much better than the population as a whole. Okay, so the approach I'm going to describe is essentially we take source code, all the examples of C, but it's not fundamental, and we convert it into a BNF grammar. But it's a very specific BNF grammar. It's a grammar that describes that source code and the legal mutations of it. We're only looking at comparison operations at this point, so we're looking at being able to change things like equals into not equals, that sort of mutation. So the grammar describes the source code and its mutants, and then we use a strongly typed GP system which allows us to cross over individual mutants and produce new ones.
So is that the grammar for this particular program, or is it a grammar for and its mutant? It's a grammar that just defines. So has it got a finite or infinite language?
So the question was, what sort of grammar is it? So I have a slide. Let's see if I can get on a bit. Whoops. So this is a fragment of the grammar. So it's a normal BNF, but it's, instead of trying to describe a language, what it's doing is it's describing a particular program. In this case, this is a fragment of the grammar that describes the triangle program, or at least a specific instance of it written in C. So the stuff here in black are terminals of the grammar. So whenever the GP system comes across stuff in black, that text will be transferred from the grammar into the source code. And At various points, we have options. So this stuff I've highlighted in red is where the GP has to make a choice.
So that's the non-terminal. Is that the only non-terminal?
These are non-terminals, but they're fairly boring.
Yeah.
So this is non-terminal that always expands to that terminal. And effectively, this is the important non-terminal, though it gets repeatedly used throughout the grammar. Did I skip over anything I should? I did, okay. Okay, so the way this is used is we analyze the source code, we generate this very specific grammar, and we feed that into the GP system, which generates mutants. So initially we generate those mutants at random. Those mutants are compiled into one executable by compiler, GCC compiler, and it produces this single image, which is essentially got all the mutants in it and a little loop that cycles through each of the mutants. So almost all of this is just mutant code, but there is a stub that wraps around it that says, okay, we started with mutant 1, now gone to mutant 2. For each of the mutants, it runs a test case, a suite of test cases, and it spits out for each mutant 2 things. So remember, we're doing a multi-objective approach. Here we have 2 objectives, and the program spits out the number of test cases that have been passed, and for each mutant, a measure of its syntactic difference from this program from the original mutated source. Those numbers, paired for each mutant, are fed into NSGA2, which is a classic multi-objective GA. And what we've done is we've stripped out from NSGA2 all the stuff that does fitness evaluation and just used its selection abilities to select from a population of mutants those that will be parents in the next generation, and NSGA2 instructs the GP on who will be parents and who will be crossed over. So we have a hybrid here between a classic GA and a GP system. So the second generation is produced from the first random population, and again we go into this loop. We run through all the mutants. For each one we produce these 2 measures of fitness, and that's fed. And so we go around this loop, which was the animation I was showing you earlier. So initially we start off with random mutants, and over time they improve. So we talked a little bit about the grammar. So for the test cases, we take this is just a triangle program, 3 inputs, and a coding that says what type of triangle it is. And in particular, type 4 means it's not a triangle. So that's the input test suite and the desired output. Just to finish off on the triangle program, what we found was of the first order mutants, about 9% of them are silent in the extent that they can take the code, but it still passes all of the test cases. The ones of interest, the hard to test, hard to kill mutants, about 8% of the first order mutants are hard to test. And as we go to higher order, both of these fractions fall very rapidly. So the fraction of 4th order mutants which are silent, are not killed by any of the test cases, is very much smaller than first order. And we see the same trend also with the desired hard to kill mutants. So the fraction of hard to kill mutants falls very rapidly with program order, with mutation order. Conversely, the center of the distribution doesn't really seem to change very much with program order. This is the same data, but instead of as a table, as a graph. Yeah, sorry.
On the previous slide, so first I assumed that because it's just focusing on comparison operators, it's going to be hard to generate equivalent mutants. But seeing as you are able to generate equivalent mutants, are your heuristics favoring or biased towards generating equivalent mutants because they would be the hardest to detect them, right?
In terms of bias, so these are exhaustive enumeration. So this is unbiased. This is literally all the first order mutants, literally all the second order mutants. That's why we stopped at fourth. So it's not a biased sample. It really is all of the mutants. Sorry, the mutants of the triangle program of this particular type. And you can see that 9% is quite a large fraction. But as we go to higher order, it falls away very quickly.
Yeah, but I meant on your GP approach because you want to minimize the number of failing test cases. Right? So on the horizontal axis, you wanted to go towards 1. So that means basically you want to find equivalent mutants, right?
Ah, okay, right, so I glossed over this detail. Okay, it's important. So one of the problems with mutation testing is producing mutants that you that pass all your test cases. And at that stage you don't know whether they're passing them because they're genuinely equivalent or because your test suite isn't good enough. What we've done is very pragmatic. We've said that if for the GP purposes, if you generate a mutant which appears to be equivalent, then it's undesirable, and we give it a penalty. So let me see if I can go back to this. Okay. What I didn't point out is up in this corner, there's a whole bunch, there are a number of high order mutants which are equivalent as far as the test suite is concerned, but we don't actually want them, and what we're doing is we're giving them a high penalty so that they get stuck up in this corner, and effectively, because they have this high penalty, their fitness is so low that they will never be selected for the next generation. So we really are driving the population towards 1 rather than towards 0.
Thank you.
Sorry, I glossed over various details. What I was going to say from this is the same data as we've seen in the table, but you can see perhaps more clearly that the center of the district. So these guys, the little red crosses are the first order, the blue one are the second order, third and fourth, and so on. And you can see, although the distribution changes, it doesn't change radically in the sense that the center is sort of between 10 and 15, even as we go to higher order. And again, I've done the trick of plotting the equivalent ones up in this corner, and you can see the figures show as we go to higher order, the fraction of higher order equivalent mutants falls away quickly. The last bit is looking at very high order mutations. So the light blue here are high order, meaning something around about 10th to 15th order. mutants. And this darker blue isn't an artifact. The data that corresponds to 10 of the test cases which are extremely effective against high-order mutants. So each of those 10 kills more than 99% of the high-order mutants. And what they correspond to, at least in the triangle problem, is they correspond to tests which test the normal operation of the program rather than the exceptional operation. And we'll see other examples where that sort of behavior comes through again. So this is a little diversion. This is a quote from DeMillo's 89 paper, talking about complex mutants, which we're taking here to mean higher order. You're saying that if you can detect all of the low order, so in our case single order mutants, then you should be able to detect, he says, a large percentage of complex mutants. Again, we treat that as meaning higher order. And what the following graph shows is not only does this seem to be true, but we can strengthen it to say that there's actually a strong correlation between how effective a test suite is against first order mutants. So going acrossways is the first order mutants, and going up is second order. And you see there's a very strong relationship. It's not just are you good at, do you kill almost all of the first order, which would correspond to this edge of the graph, but actually at any order, if you're good against first order, then you will also be good against second order. And the same thing more or less holds with the relationship between second and third order. And it's not no claim to novelty, it's just it's nice to back up statements that have been put out as sort of hearsay with data. Conversely, the competent programmer hypothesis, we haven't really got any data here, except this, well, the original claim was that if you errors, meaning bugs, should be detectable as small deviations, so it should be detectable as first order mutants. But what people have actually found is when they study real large software engineering systems, so these Customer and Perry looked at source code, I think something of the order of 10 million lines of code. And what they found was overwhelmingly the bugs that remained after testing required multi-line fixes. So in our view, the serious bugs actually correspond more to higher order mutants than they do to first order mutants. Any questions? Is this clear, or you all agree, or you think these guys are idiots? Okay. I was going to skip past the stuff on schedule and TCAS in the interests of time, and go on to gzip. So gzip is a fairly old piece of Unix code, about 6,000 lines of C, been heavily optimized. But in contrast to the other benchmarks, we have relatively small test suite, so only 200 odd test cases. And that test suite exercises the code very non-uniformly. So the point of this graph is to emphasize that effectively. So there's a line of first order mutation locations, so these are comparison operations, which are not tested by any of the test suite. So that's what the 0 there means. And then there's a scatter with an average value of about 24, and then there are some mutation of sites which are tested literally millions of times. It seems very dubious that you actually learn any more about the quality of the software after a million tests than you do after the first million. But anyway, that's the way the test suite is organised. What we did was to say, well, okay, this is going to be a bit tricky. We've got the whole of gzip to look at, and most of it is not being tested. So what we did was to restrict ourselves to the mutation sites that are run by at least half of the test suite. So more than 106 test cases. And so we're deliberately restricting ourselves, so we're not looking at the whole of gzip, but only the well-tested parts of it. And what I'm going to do is look at two cases of interaction between first-order mutants. The first thing to say about interactions is the second-order mutants formed by simultaneously performing two first-order mutants are almost all pretty much the same as the original first order. So that's what the red dots here are trying to say. The red dots here are second order, and almost, well, those, apart from the ones I've highlighted, there's not really a lot of difference between the first order and the second order. And quantified, not much difference. I think there's a difference of 4 test cases. 4 test cases out of 200 odd. The first exception I'm going to look at is this guy, which is formed by the interaction between two first orders. So individually those first order mutants are easy to kill, but when they are put together you get something which is more difficult. So I'm trying not to go into too much detail with this. So the first is this guy, is a test for is count less than min count, and what we do is we replace less than with less than or equal, and that immediately breaks the count, and 89% of the tests fail immediately on that. The other one is we replace, well, it's in the same routine, it's about 13 lines later, we replace equals with not equals, and again that immediately breaks 99% of the test suite. What this one actually does is reverse min count is set equal to 3 with min count is set equal to 4. So those are two clauses in the same else. So replacing not equal equals with not equals means we reverse the order of the things in the else. But then we get and then that breaks everything. But when we put those two together, we actually get masking between them. And the mechanism whereby this happens is in many, well, maybe about 30-40% of cases, this, if near the beginning of the loop, actually boils down to is count less than 4. And the effect of introducing this mutation is instead of setting count to 3, we set it to 4. So what we're effectively doing is replacing, or at least in many cases, we're replacing if count less than 4 by is if count less than or equal to 3. So there's about 30% of the test cases where this analysis holds, and what was previously a highly fatal mutation becomes more difficult to test against. So after applying both those two together, we now pass approximately half the test cases, whereas individually we failed overwhelmingly all of them. The second example is the opposite. So again, I didn't highlight it on the first slide, but what we're looking at is these second order mutants, which are each produced by adding together two first order mutants, which originally passed all of the test cases. So these guys appear to be equivalent, but if you change the code elsewhere, it suddenly starts breaking. I'm not going to go through all of them, just one of them, again, try and explain it quickly. The first mutation is we take a not equals near the beginning of the loop and replace it by a less than. And that makes no difference as long as the things we're comparing are both positive. But there is a number of cases where the not equals is comparing something which is negative with something that's positive. And so that makes a difference. But if we just made that change, the difference would be trapped by code later on, and we wouldn't see the difference. So we were talking this morning about fault masking. If we regard this as a fault, then if it's the only thing that's happened to the code, then that fault doesn't manifest itself. It's the fraction of cases where it matters are caught by code later in the same routine. The other one is much more what might be regarded as a classic equivalent mutation. We take greater than and replace it by greater than equals, and that has the effect of, instead of returning the first string that satisfies that condition, it returns the last string that satisfies that condition. It doesn't make any difference apart from perhaps a minor difference to runtime. But if we apply both of these mutations, then this operation, which succeeded in masking that mutation when there was only one of them, is suddenly broken. And we go from two first order mutants which were entirely equivalent, all the tests pass, to something which fails almost all of the test cases. So again, we have surprising interaction between first order mutants.
Excuse me, that sounds impossible to me, like that. So you make one change and you end up with two equivalent programs, and then you can change the second one and get a third equivalent one. Surely the first one's equivalent to the third one.
So when I talk about this second mutation side, what I mean is we apply, at first order we just apply that one. And at first order, we just apply the first one.
Oh, so you're applying them both to the first one, and then...
So first order means take the original and make one change to it. And that's... So both cases, if we make one change to it, then it still passes all of the test cases.
Are they equivalent in general? Are they really equivalent, or are they just equivalent with respect to that test set?
From my limited analysis, I think they really are equivalent. It may be that I overlook something. This is fairly convoluted code, but I believe that they are equivalent, yes. The first one, part of the reason for having a not equals there is for efficiency, to break out of a loop early on without going into the whole thing to check all the conditions. This is later in the same loop, and the effect of it, don't think the program designers had this in mind. The effect of it is actually to catch the few cases where the first mutant makes a difference,